Well, good morning, good afternoon, good evening, everyone. Welcome to the 11th Digital Twin webinar. And this webinar, we're going to focus on economic impact of climate change. This is also origination from one of the sessions we had in July at the International Symposium on Spatial Temporal Data Science, which is co-chaired by me and Dr. Sumin Bao, who's also helped us co-moderating today's webinar. And Dr. Bao is the director of Child Data Institute at Michigan, Ann Arbor. And I'm Phil Young. I'm a professor at George Mason University. We're fortunate to have four distinguished speakers. We're going to introduce one by one when they do their presentation. So our first speaker will be Dr. Laura Dickinson. She's from University of Arizona, the public policy school, has done a lot of research on the economic impact by climate and other disasters. So Dr. Dickinson, please share your screen and take it away.
Many thanks. All right. So welcome everybody. It's wonderful to be here today. So I'm going to talk broadly about the economic impacts of climate change, but through the lens of one specific project that I have worked on, looking at the impact of tropical cyclones on economic growth, and of course the impact of future climate change. So broadly, just to kind of set some foundations, we would expect the economic impacts of climate change and importantly focusing on natural disasters in particular to be kind of co-determined by several broad factors. Of course, the physical effects of the disaster themselves, the wind speed of the hurricane, the rainfall from an extreme precipitation event, etc. But also layered on that is what's in harm's way, the infrastructure, the people, the economic activities, and also the adaptive responses that they take either well in advance or immediately surrounding the timing of the disaster. So because of that, we can kind of envision that there's many economic impacts of climate change and natural disasters in particular, but we would expect a lot of heterogeneity across the different disaster types. Cyclones versus heat versus drought, and also the individual sectors that are being impacted. So thinking about agriculture, fisheries versus manufacturing, commerce, tourism, the broader environment. And also how individuals, firms, and policymakers respond to these threats. All of those are kind of important ingredients when we're thinking about modeling disaster impacts and importantly, kind of counterfactual states of the world, right? Thinking about changing climate, thinking about change or the characteristics of the extreme events, thinking about how human communities may also change on their own endogenously over time, and also how adaptive responses may change over time with new technology, et cetera. And so, engaging these types of models, I think, is very much in the spirit of this webinar series, thinking about drawing heavily on interdisciplinary insights, large data sets to really conduct careful modeling. And these types of models then can produce some very important and policy relevant parameters or outcomes. So understanding better the social cost of carbon, to the costs and benefits of adaptation, and also, as we're interested in this paper, looking at the overall economic impact. So how might we expect this to impact gross domestic product? So I'm going to kind of briefly, given the time today, overview this paper because I think it draws out quite a few of these themes. It's joint with Dr. Lint Barrage at ETH Zurich. So that's a bit of a motivation for this paper. So what do we do in particular in this paper? We're really interested in this question of how tropical cyclones affect macroeconomic outcomes like growth. So how the gross domestic product or GDP changes over time. And importantly, then, what will the effects of climate change be? We know that tropical cyclones are one of the leading causes of natural disaster damages worldwide, including in the United States. We, just with Hurricane Helene, again experienced their decimating impacts. And we know that cyclones are one of the types of natural disasters that will be significantly impacted by climate change. So we, previous work has carefully estimated that we expect damages to increase as well. And there's a very rich empirical literature built on really good, high quality empirical data, spatial data, socioeconomic data, but finding looking historically at historical hurricane and tropical cyclone activity and impacts on national level growth rates, GDP growth rates. But the empirical findings have been quite divergent from positive relationships. So cyclones leading to higher growth rates to null results all the way to large negative consequences. So one of our first questions of interest in addressing this challenge is, why might there be such variation in the approaches? Importantly, too, we kind of identify in this paper what we call this micro-macro gap that's, again, been well known kind of in the literature. We're not new to be identifying this. But the fact that, this really rich data-driven empirical evidence has a more limited connection with macroeconomic theory and limited integration with climate economy models. On the flip side, we also find that, there's again, these empirical results are not very often incorporated in climate economy models. And more than just tropical cyclones, we see these types of careful empirical approaches across a broad spread of natural disaster types. So temperature shocks, precipitation shocks, etc. And so as I mentioned, like fairly limited incorporation into climate economy models, although there are a few nice examples. And on the other hand, there also are this can be seen as a potential challenge with the climate economy models to the extent that they're, theoretically rich, but aren't based heavily on, careful empirical data. And of course, many try to be or attempt to be, but there could be some real challenges integrating, careful empirical work into these climate economy models. All right, so what do we aim to do in this paper? We first of all put together a modern, harmonized global data set of cyclones and growth in order to revisit a lot of these classic empirical approaches and specifications to see how much of them may be driven by examining the divergence in results, may be driven by examining different cases or countries or time periods. So we wanted, a harmonized global data set. And then also use an empirical lens to try to perhaps shed some light onto why these empirical findings may very logically come to different conclusions. And for example, we find that when disaster risk or cyclone risk is operationalized as the long run average of landfall events, here we might theoretically expect to find a positive correlation between growth and disaster risk. Versus based on the theoretical lens, a cyclone strike would be unambiguously negative on GDP growth. We then offer a modified empirical approach. Instead of looking at the empirical question of how do cyclones impact GDP growth, we instead look at how cyclones impact the structural determinants of growth. So these kind of core pieces that go into determining growth. So things like capital depreciation, human fatalities, and also total factor productivity. These components, very carefully estimated in empirical data, then can be directly embedded into a cyclone climate economy model. And so we kind of provide a proof of concept example in the paper quantifying cyclone climate economy models for specific to each of 40 cyclone vulnerable countries. We then can let the model kind of endogenously look at responses and adaptive behavior and then project the impacts on the overall aggregate economy and therefore project the impacts on aggregate growth. All right, so just to very briefly think about what our theoretical model is, because I'll highlight a few insights from it in my talk. We important to note there are multiple different flavors or versions of growth models. So we selected a growth model that we found best fit the empirical evidence that we were observing. So that was most closely to Krebs' set of models. So we assume that there's this aggregate, this country with aggregate production that's based on human capital, physical capital, and then this A factor, this is the total factor productivity, that kind of scales these inputs into total output. This economy can be hit by a cyclone strike, realizations that can harm all three of these kind of structural determinants of growth: human health, right? Mortality and human capabilities, physical capital, as well as total factor productivity. We also allow for insurance in this model, although typical with the state of kind of global insurance on natural disasters, we assume that these markets are incomplete. All right, so now I want to overview our kind of harmonizing approach to look at the empirical evidence on cyclones and growth. As I mentioned, there's a wide range in empirical findings, although the studies are arguably very carefully done, but they differ on a lot of components. If they use cross-sectional versus panel data variation to look at this, these responses, and also how they operationalize the cyclones themselves. Do they use meteorological measures of wind speed or precipitation? Do they use kind of damage or outcome measures to operationalize? Fraction of capital stock destroyed, fraction of population that perishes, and also the sample, the time period, the specific countries. All of these theoretically could lead to different types of results if we expect that there may be heterogeneity in these responses. So again, motivating why we wanted to develop a comprehensive modern global data set and revisit some of these standard specifications within this harmonized data setting. So that's exactly what we did. We collected the full history of available storm records from the International Best Track Archive for Climate Stewardship. They collect cyclone information and validate across many different sources, many different countries, World Meteorological Organization and others from 1970 to 2015. And we look at county by storm landfalls, looking at the counts, the maximum wind, and also the energy. We then collect a lot of macroeconomic indicators through the World Bank and Penn Table, including educational investments, in human capital, geographic indicators, spatial controls, as well as direct cyclone damages, both from the MDAT's disaster impact database and for robustness insurance estimates through Munich Re of losses. So firstly, we look at cross-sectional specifications. So this is looking at in line with what previous literature has found. So a very famous paper in this area, Skidmore and Toria's 2002 cross-sectional paper, they found this positive association that countries that receive more landfalls on average in the long run also correlated with higher growth rates. And this is controlling for some additional factors. And so we rerun this kind of classic cross-sectional long-run average cyclone risk with this kind of standardized data set. Of course, omitted variables might be a concern here. And so that might be relevant for the climate effects and could be influential in the findings. But however, with that said, we still replicate this positive correlation. So in the long run, finding on average, countries that received more cyclones also had higher growth rates. So what theoretically might give way to this sort of finding? Again, through the lens of a theoretical model, we're able to kind of look at a few of the different channels, and it's theoretically ambiguous if in the long run cyclones should accelerate or decrease long run growth. So of course, unambiguously, the third effect, the depreciation effect, cyclones, all else equal, will accelerate depreciation to human capital and physical capital. This unambiguously should lower growth. The other two, so the first factor, the progressionary savings effect, if storms motivate people to save more in a precautionary sense, this could lead to higher growth rates relative to counterfactual with no storms. And then thinking about what that savings is invested in could go either direction, increase or decrease growth rates. So if people are encouraged more to save in high risk but higher return investments, this would increase growth rates, and just the opposite if lower risk, safer investments would lead to lower returns and therefore lower growth. So really, theoretically, it could go in either direction, and it becomes really this empirical question. There could be non-monotonicity even over time within the same economy. And really, these positive effects likely are driven through channels like increased savings and education. So we also wanted to look, and indeed, in looking at columns 2 versus 3 and 4 versus 5, once we add in some of these proxies for investments in human capital, i.e. Schooling rates and also savings rates, we see that these estimates of the positive impact are, again, suggestive evidence that some of these theoretically motivated channels, we're seeing them in the empirical data as well. And we also do find these nonlinearities that it may, we might expect some kind of like turning or tipping points where, this isn't only a positive relationship, but we may see some kind of curvature to that relationship, as well as theory predicts this kind of ambiguity between long run positive and negative effects on growth. So, but critically though, and is well known, gross domestic product is not synonymous with welfare. And so we also highlight that these countries receiving more cyclones, even though they are their GDP growth rates may be higher than countries receiving fewer cyclones, unambiguously, they were worse off from a welfare perspective. So I think that's still an important thing to note, that higher precautionary savings, for example, or investing in these riskier types of investments than you would have done otherwise in the absence of the long run cyclone risk doesn't make you better off. So from a welfare perspective, it's clear that these countries and individuals are still worse off. We also then turn to a panel fixed effect specification, which is by far a majority dominant approach empirically to examine these relationships. And the idea there is, instead of looking at long run cyclone risk, they look at cyclone strikes, individual cyclone events. And here's where we find a lot more consistency in kind of negative relationships between cyclone strikes and growth. Although I will note some find more muted or insignificant results. So we run a very similar panel fixed effect specification. And importantly, I think of relevance to this audience, we also look at two different versions of our country sample. So we include in one base version all countries we have data on. And then we include in a second version all countries that we have data on, specific country by year control variables. Importantly, we don't include these control variables in the regression, but we purely want to see, is there a sample selection difference between using countries that arguably have higher quality data and countries that may not have as high quality data. So just purely driven by different samples, do we see differences in these empirical results? If so, then that could be one factor also driving these divergent results. And actually, yes, we do. So the first three columns, we find these unfiltered results with all countries that we have just fundamental data on cyclones and GDP for, and some very, a couple additional variables on access to credit and whatnot. We don't find any significant relationship. However, once we move to the smaller sample of countries that would have high quality control variables available, we find very significant results and negative results, right? As expected, that cyclone strikes are harmful to economic growth. But importantly, we also find heterogeneity. So we find that this negative relationship is attenuated by higher income countries, and also countries that may have better access to credit. So again, some of these theoretically motivated channels. And again, kind of just highlighting the importance of underlying data in kind of understanding what you're estimating and in who's really in your data sample. As maybe as you may have anticipated, across these kind of all country versus the countries that have controls, we see significant differences. The countries with controls tend to be larger, have higher capacity, and higher growth rates. All right, so then that brings us to kind of our theoretical propositions that cyclone strikes should decrease growth, but cyclone realizations, long run cyclone risk may have a more ambiguous relationship. Importantly, we don't find in our global sample any sort of rebounding effect where near term growth rates are accelerated. As a point of comparison, some alternative types of macroeconomics, like the solar growth model, that's a very fundamental ubiquitous model, would predict this, like if growth rates were temporarily below average, kind of long run fundamental average, it would anticipate this like kind of rebound effect of like higher growth rates to cancel that out. That's not what we're finding in our data. But again, just noting that there can be multiple theories, right? Macroeconomics isn't dominated just by a single theory. All right, so that was kind of our review of the empirical approaches, and again, kind of the major points, I think very relevant for this group is, there's a lot of factors that can lead to, very high quality research coming to very different conclusions on this key question: what's the impact of cyclones on economic growth? And importantly, it couldn't be underlying, specifications, it can be data. It also could be that they're just examining different parts of that overall growth equation. So, results that seem to be in tension through the lens of theory, in some cases, may be ameliorated. So it might actually make sense. It's not in conflict that we find negative results in some specifications and positive results in others. All right, so we then proposed, this last kind of exercise we did in this paper was to then propose an alternative. Instead of empirically asking, how do cyclones impact growth, which is more of a reduced form approach. So it may miss some of these structural feedback mechanisms that might be very important in the economy. We instead suggest to estimate very carefully, again, with this comprehensive data set, the structural determinants of growth. So how cyclones impact those, how cyclones impact total factor productivity, capital depreciation, and also human capital depreciation or mortality as we operationalize it. We can then embed these carefully estimated parameters directly into our cyclone growth model. So we do exactly that. We look at the impact on total factor productivity and find, importantly, negative impacts for several years. And so what is total factor productivity? It's kind of the technology and processes that convert these inputs, so human capital, physical capital, into the output. So disruptions to TFP could be things like electricity outages. Maybe your workers or your factory isn't harmed, but there's an electricity outage, so you just can't use them. That would be seen through this TFP channel. There could be complementaries in production, so maybe your airplanes are all unharmed, but your airport runways are harmed. So again, this would be a disruption in that. And of course, there could also be interlinkages with other types of depreciation as well. We also rerun, very classic to the literature, damage functions for property losses and fatalities. We also allow for heterogeneity based on some well-known vulnerability characteristics, population in harm's way, and also overall GDP level. So, and we find very logically that higher GDP countries have less of a damage impact. So this is a kind of an adaptive response, and countries with more population in harm's way, in these kind of low-lying areas, also have higher GDP impacts. But overall, again, we find, no surprise here, replicating previous literature, the very strong damage elasticities. So property damage is increasing to proportionally with wind speed, Interestingly, in the United States, we find, and I found this in previous work as well, that this kind of damage elasticity is much higher. So it's a damages rise to the fourth power of wind speed in the United States, as opposed to the global average. All right, so we then embed this in our cyclone climate economy model. One more important piece, and again, using more, kind of careful data, we need to estimate how the cyclone risks are going to change. We don't want to just use changes in mean or average cyclone risk. We actually want to be able to predict the full distribution of cyclone realizations in order to kind of randomly draw from that and get a sense of this total distribution rather than just the mean effects. So how do we do that? We use Carrie Emanuel's synthetic storm tracks, randomly seeded, assuming IPCC A1B, and NOAA's GFDL global circulation model, so 34,000 simulated storm tracks, and use a Monte Carlo simulation then to estimate these probability density functions for each country. And so here's kind of what they look like, the current in dark colors, and then the future in white bars. I will note, I think there's a lot more that can be done here. So I'm sure some of you are, already are getting ideas for how to add to this. This was more of a proof of concept. So this only looks at wind speed. We don't look at sea level rise. We don't look at precipitation. Clearly, these are critically important components of cyclone impacts as well. And importantly, we see while overall, and this is through 2100. So of course, past 2100, the impacts will be different. But we see most countries will expect their PDFs will shift to the right. So these disasters will be getting more intense with higher probability, but we do see some heterogeneity. So there are some examples of countries where mean wind speed from the data will decline. Again, this is more of a proof of concept. We could use more modern, the cyclone tracks that we use are a little bit of an older vintage. So I think there's more work that can be done here. All right, so then we put this into our climate economy model. And importantly, we also allow for this heterogeneity in household choice decisions about how much they consume, and also investing in human capital versus physical capital. This is to explicitly get at some of these endogenous response channels that I mentioned before. We also calibrate the model using empirical data and also kind of globally standard parameters from the literature and do sensitivity testing, of course. And so super briefly, because I know we're almost at the top of the hour now, we find, significant growth impacts. And so this is the long run impact of climate change on economic growth. So GDP growth, and, kind of no big surprises here, but, small islands tend to dominate this list. Also, the United States, as I mentioned, is very vulnerable in terms of the sensitivity to high wind speed increases. But importantly, also we see that, so in the dark black bars are just the climate change effect alone. But we also allow for these endogenous vulnerability responses, and we find that these adaptive procedures do matter when thinking about this. So if we just took the plain climate change effect, we may be overestimating those kind of key results, because economies change and people and policymakers are going to be endogenously responding to these shifting risks as well. Importantly, remember, growth is not synonymous with welfare, so we also look at specific welfare effects, and again find kind of similar results of, small islands, and the overall climate impacts are kind of mitigated by some of these endogenous responses to change vulnerability, reduce vulnerability. All right, so I will stop there, but I think, just big picture for, that might be of relevance to this webinar audience is just thinking about those connections with how to best use the incredible data resources available to answer some of these really challenging, complex questions. And so I think one theme from this project is really the need for, careful interdisciplinary work and insights, but also the interplay between theory and empirics. So, using theory to guide empirical approaches, but on the flip side, using rich empirical results to better guide and calibrate theoretical models as well. So I will stop there for now and happy to field questions for a couple minutes.
Thank you, Laura. That's very insightful and very deep on the research. In fact, I know that data availability probably is one of the problem. So look into that. I think probably you looked more into the wind side. Did you consider other climate-related disaster like flooding or other disasters?
Yeah, no, so great question. So in this particular project, we only looked at wind, but completely agree. Only a partial view, right? So I think a complete analysis, you'd want to include precipitation, you'd want to include storm surge, you'd want to include sea level rise. So I think this was kind of more of a proof of concept, but I think the kind of underlying approach would be very applicable to all of the, incorporating all of these elements of cyclone risk, but also apply to other types of climate risks. So thinking about heat, thinking about extreme precipitation, tornadoes. And so I think that, there's a very good future for exactly this sort of work. But yeah, we kind of took a more basic approach in part because of data ability as well. So I know that it's as global cyclone data has actually matured quite a lot when being able to synthesize with precipitation estimates, synthesize with surge estimates. But this is an interesting case where you need really high quality historical data across as broad of a scale as you can get, in both, geophysical and atmospheric measurements, but also human data. So, high quality, GDP data, as well as a lot of, control variables or other things that may be moderating these relationships, but then also being able to project ahead to, have, careful high quality estimates of what storm surge might look like under different sea level rise, assumptions and whatnot. So I think it's a really exciting area for exactly this type of audience as you all to be thinking about really how to the challenge, but also the opportunity to kind of synthesize and integrate all of these pieces.
Yeah, thank you, Dr. Bakinson. We have time for one or two more questions from our audience. Anyone? You can unmute yourself or put your question in the chat window. Luis, please go ahead.
Thank you for the talk, Dr. Backinson. I guess my quick question, in your analysis, you used a pre-existing climate data on storm tracks. I'm curious if you have any thoughts on either the approach they use. I think that's based on a single model, and a lot of the science has moved towards using an ensemble of models, so you kind of expand the number of universes or Earths that you or realizations, right? So that you have information for. Do you have any thoughts on how this work could be extended to take advantage of that approach and then that sort of wealth of data, and how to deal with sort of suddenly you have all these sort of many realizations of the world, which maybe it's useful for the Monte Carlo simulations you're using. But yeah, I'm very curious about your thoughts on that.
Yeah, no, I think that's a fabulous point. So again, I think this was more of like a proof of concept approach. So technically we have simulated storm tracks for 3 additional general circulation models. So not just NOAA's GFDL model, but 3 additional kind of globally recognized models. So we certainly could have, and we had just picked NOAA since it was a major model, but absolutely, and I think there's key pieces where you could think about adding more to get kind of this portfolio or compendium of what the results say. So in some of my other work, we have used all 4 of the different models. Again, that's only 4, right? It's not like there's even more GCMs out there, but also other points of variation would be the climate path, right? So thinking about RCP 4.5 versus 8.5, and then also I think the kind of bigger bottleneck is, and there may have been some more advancements recently, but the particular model to generate the storm tracks, right? So Kerry Manuel's Windrush Tech LLC, they've been kind of the bigger player in this game historically, but I think that may be changing. More groups are starting to like develop their own simulation models. But yes, absolutely, I completely agree. I think there's multiple points where you could add a lot more complexity and really to see what difference that makes, right? Are we seeing harmonization of these results? Are we seeing divergence in the results? So yeah, I think that's a great point.
Thank you,
Thank
Dr.
you, Lauren.
Professor. Pick. Now we're going to turn to Dr. Sumin Bao, the director of China Data Institute and also the co-director of the Harvard Spatial Data Lab, to introduce our next two distinguished speakers. Dr. Bao, please go ahead.
Thank you, Phil. And so our next speaker is Dr. Martin Rammer. And Martin received his PhD in macroeconomics in France in 1985. Martin is a former World Bank chief economist for the Latin American and Caribbean region. And he has been served for the World Bank for almost about 30 years. His topic today is measure global economic activities using air pollution. So Martin, now you can share your screen.
Thank you. Thank you very much for the kind introduction. Yes, let me move on to sharing my screen. Oh, sorry, I got the wrong screen.
So you have 30 minutes for presentation, and then we have 5 minutes for questions and answers. Yeah.
Yes. Can you see my screen?
Not yet. Yes. Yeah. Good.
Okay. Thank you. So this joint work with Daniel Riera-Krishnan, who will be a panelist later in the session today, with Stephen Morris, who is at Amazon, and Irene Esran. And this work we started conducting when I was the chief economist for Latin America in the World Bank. Let me tell you what I will try to cover in these 30 minutes. First is why we do this, and I will add a bit on how it can relate to climate change, although it's not directly about climate change. Then the data we use, which is relatively novel data, NO2 data. Then the analytical framework, the results. And I will not speak about the future work because I believe that Daniel will be elaborating on that. So what is the motivation? When Laura was presenting her paper, she was talking about good quality GDP data. And good quality GDP data is, of course, essential to measure economic impacts of climate change and economic impacts of any important shocks. But I will argue that is even more important in the case of climate change, because some of the countries affected, most likely to be affected by it, some of the most severely affected are poor countries where the GDP data is not particularly good. So what are the limitations of GDP data? And I'm not even going to welfare, as Laura said. This is just economic activity. First is that statistical agencies tend to have limited technical capacity. And that's especially so in developing countries, which will be the worst affected.
Sorry, Martin, are you moving your slides? Are you changing your slides? We didn't see your slides changing.
Oh, I was. Let me try again.
Maybe you have the different screen.
Yeah, how about now?
Now it's moved to the second one, right? To the third one.
Okay.
Martin, you probably need to share your presentation screen. You are sharing the PowerPoint screen.
How about now? Do you see it? Do you see my slide?
We see the PowerPoint, but it's not in the play mode.
It's not in play mode?
Yeah. So maybe you are tonight to share your screen. You maybe close this share and then reshare that, share your screen.
Yeah, sorry about that.
Not share your PowerPoint.
Yeah, I'm sorry about that. Let me
No
try
problem.
again. Do you see it now?
Are you in the play mode or?
Yeah, I think so.
We cannot see your play mode. So you probably need to, so this is your original PPT, not in the play mode.
Yeah, so maybe I'm doing something wrong. Can you share it from your side? I had sent it, and I can.
Yeah, let me try if we can share from my side.
Yeah, I don't know what is happening. Sorry about that. Today we tried and it worked. So I don't know what's happening.
Now, when you use a play mode, they will probably have the two screen.
Okay, I'm going to share from my side. So Martin, you just need to tell me next.
Yeah, sure. Thank
Okay.
you very much. Yeah, is it? So I already mentioned who the authors were. Next slide is the structure of the talk. And I said that the future work, Daniel will be talking about it. Next slide. And next slide, why the motivation? So Laura was mentioning GDP, good GDP data is essential to measure the impacts of climate change and any other shock. And the issue is that for some of the countries that will be most affected by climate change, these are developing countries where GDP data is not particularly reliable. The typical problems with GDP data are that statistical agencies are not technically strong, that especially in developing countries, it's difficult to capture informal economic activity, and sometimes most economic activity is informal, that very few countries, developing countries, have subnational measures of GDP, and some of them are very large. If you think of things like cyclones or extreme weather events, they can be much more localized than when you can capture through aggregate GDP. There is low frequency of the data. Typically, it's annual data, not quarterly data, and with substantial delays in publication, even in advanced economies with significant revisions over time. And then data and GDP can be manipulated for political reasons to declare victory on this or that, or to try to claim that this country is doing worse than it's doing, or whatever it is. So for all these reasons, one has to approach GDP data with some dose of skepticism. Next slide. So there have been different ways to try to improve on the reported GDP, and some of them boomed during the pandemic when there was a need for real-time measures. There are experts and sectoral surveys. There is a lot of data that is coming from smartphones. There is data on power consumption from utilities, power utilities. And then what has become increasingly popular is nighttime light data from satellites. Next slide. There are limitations to these approaches. The surveys are very heterogeneous, so cross-country comparisons become very difficult. Smartphones, again, if you're dealing with developing countries, not everybody has a smartphone. The utilities, a lot of people may not be connected to the grid in developing countries because they are too poor. In advanced economies, they can be on their own systems. So what remains as the most promising, and that's the line in which our paper participates, is satellite data, and that's where we find the largest number of applications when it comes to GDP. Next slide. These are our paper. These are our contacts if you want to look at the details, because it's quite technical. I will only touch on the big picture. Next slide. So the data, the next slide, NO2 data. NO2 is a plausible measure of actual GDP. NO2 comes from combustion, and a lot of economic activity, fumes from chimneys, exhausts from vehicles have combustion. They last for only a few hours, and they stay near the source. So they are very localized in time and in space. They are always measured during the day, which is when most economic activity occurs. Night lights, of course, is at night. They are measured with a high spatial granularity, and one can have open access to it even on a daily basis. Next slide. In our case, we in this paper, we use data from Earth Observing Systems EOS from or a satellite. Is part of the A-Train constellation, is that it's crossing the equator on a pole-to-pole route at around 1:30 p.m. every day. And we use the vertical column densities from the ozone instrument that are very precise in the measurement. These columns are quite high. They go to like the maximum. They have a very high spatial resolution, 24 kilometers at the nadir. Next slide. Yes. So here is an intuitive application. This is what happened during the COVID pandemic. When you have the darker blue, it means a stronger reduction in NO2 emissions. This is what you can see in China between the beginning of the pandemic and the previous year. Next slide. This is what you can see during that time in Europe. And next slide, what you can see. Next slide, yeah, in the US. So this is just to motivate that it seems to be capturing what is going on, some change that is going on. Next slide. It also offers interesting depiction of what happens with economic activity. So here you have for the entire world 2 moments of shocks, not climate change, but important shocks, and the same logic can be applied to shocks that come from climate change. You see the financial crisis and the pandemic, and you see that NO2 data captures very well the change at the global level in emissions that is associated with these 2 shocks. Next slide. You can see it also in a more disaggregated data. In this case, is China. You see again, and the pandemic, and NO2 data captures that very clearly. You don't see the same thing if you look at lights data. Lights data tends to be more stable, and especially the more advanced the country, the more stable lights data are. Next slide. So what we do first is to show that other indicators of GDP, of economic activity, lose significance once we introduce the controls. If you could click fill so that I can highlight this as small animation. Click for one more slide. Yes. So you see that if you, thank you, if you only take one indicator, NO2 emissions or lights or CO2, electricity from the power grid, or the survey of opinions, all of the indicators are solid predictors of GDP as we measure it. So you would say they are all good. However, on the right side part of the slide, you will see that we introduce more controls. Click again, Phil, please, next slide, so that we see the animation. And you see that, for instance, lights, which are the preferred instrument, lose significant as soon as you enter the other controls. So this is a suggestion, and while NO2, next slide, NO2 remains completely significant. So nighttime lights are really significant when statistical systems are weak. And here I want to introduce these categories A, B, C, D, E, which is a classification that comes from the World Pen tables on the quality of statistical systems. So when you take all the systems, all the countries, A, B, C, D, and E, you find that NO2 is significant and lights are significant too. But when you go, and the same if you take the categories in D and E, which on the last column, where lights remain significant. For all the intermediate range, basically the lights lose significance. Next slide. Yeah, there you see what happens to the lights. And next slide. Yeah, so here is the data we use in this paper. We have 178 countries, but in fact, the classification is for 175 countries. We have a number of years going from 5 to 20 and some more information. I will not take time on this because my mistake, I took time in the uploading of the slides. Next slide. So what is our framework? Next slide. The framework is based on two of the canonical models in this literature, Chen and Nordhaus, 2011, and Henderson and co-authors, 2012. And this is a very simple model. It has two equations to begin with. The first one is where Z is the GDP as we see it in the statistical systems, and Y is an unobservable actual GDP, the thing we would like to know. And epsilon shows that there is measurement error, and the measurement error depends on G, which is a group of countries, A, B, C, D, or E. You have different kinds of measurement error. The second equation has as the left-hand side variable the satellite signal. Can be lights, can be NO2, which is also related to the actual GDP that is unobservable and has its own measurement error related to the satellite. So if we replace Y from one equation into the other, we get one equation that works on observables, which is that the log of reported GDP is related to the satellite signal, in this case, NO2, through this coefficient 1 over beta, plus an error term. Next slide to highlight one point here. This can be used with the error measurement framework to predict, so what is our best prediction of the actual GDP, the Y hat. And our best prediction is weighted average, weights lambda G and 1 minus lambda G of the satellite signal we get, Z, and the predicted, of the GDP we observe, Z, and the predicted GDP that comes from our estimate. And the lambda, the weight, depends very much on the measurement error of the statistical system. So it has to do with the variance of the various indicators, but you have in the denominator the measurement error of the statistical system. The weaker the statistical system, the bigger the weight you have to put for the predicted GDP, the actual GDP that you are trying to estimate, the bigger the weight that you put on the signal that comes from the satellite, which is intuitively makes sense. Next slide. So how is this estimated in practice? Is the observed GDP in some place at a time t, country I, and when you do it with lights, it depends on you have different satellites and different sensors, so they control also for the kind of sensor, is a function of the signal you are getting from the satellite. And then there are controls for time, for country, for sensor, and an error term. The problem with this specification is that the error term by construction is correlated with the dependent variable. If you click on one more slide, it can highlight what the problem is. Next slide. Yes, so you see that you have on the left-hand side, you have the GDP in this equation. On the right-hand side, you have something that is related to the quality, the measurement error that comes from the statistical system. So how to deal with this problem? This is a problem of homogeneity. Next slide. There is a standard approach to it. And it comes from Henderson and co-authors in 2012. Basically, you have a system that has, let's say you have G levels, in our case, A, B, C, D, E levels of statistical capacity, and the data gives you 2 plus G moments, and these are the equations you have there. But you have to estimate 3 plus G parameters. So you have 1 degree of freedom. And what Henderson and co-authors do is to assume that for the countries at level A, the best statistical system, there is no measurement error. And so they impose no measurement error for, say, countries like the US, and based on that, they bring back down the number of parameters to estimate to 2 plus G, which is exactly what needs to estimate. Next slide. So we use our innovation to address this issue is that we have 2 signals. We have NO2 and we have night lights. And we saw that both are correlated with GDP, but it is plausible that the measurement errors are not correlated with each other. And that's what you need for a good instrument. Why? Because one is measured during the day, the other at night. There are different satellites, different sensors. So there is difficulty in thinking that these errors are correlated. The only correlation is that the observations excluded, which tend to be due to cloud coverage or to auroral activity, can be similar. They do not overlap completely anyway, but you can say, oh, the days excluded are the same. But so this hypothesis, the using of an instrument, gives an additional moment, and so we don't need to impose now that the statistical system, the assumption that the statistical system of advanced economies is perfect, which we were doing, and that will make a difference, as you will see. Next slide. So what are our results? I think I have 9 minutes. So we take the variable that we're using is NO2 as the explanation, and we can instrument just by lights, second column, or we can add more instruments. So to repeat that with more instruments, assuming that they could be uncorrelated. The most interesting one will be just with the lights. If you click fill again, I can highlight a couple of points in this table, so it's not too dense. Please click on the next. Yes. Yeah. So you see there is a big difference in the estimate compared to the kind of Henderson estimate when we introduce the first instrument, which is light. On the other hand, click again, please. If we add more instruments, we don't get too much of a difference. So basically what we do in what follows is to just use lights as an instrument there. Yes, next slide. So what we find is that, remember that the best predictor of the actual GDP was a weighted average with weights lambda and 1 minus lambda on the actual measured GDP of the statistical system and our predicted GDP based on on the signal from the satellite. And there you have the 5 levels of statistical systems from A to E. And you see that the measurement error in GDP increases, of course, as you move from A to E. And the weight declines, the weight that you have to attach to official statistics. So if you take E, you see that the weight you will put into the official statistics in some of the poorest countries is just a fifth. And the other 4/5 you have to take it from the prediction from the satellite instrument. But even if you look at countries like A, advanced economies, it's still not 100%. So you still improve on the quality by using the satellite imagery. Next slide. So that's the point I was making, that decline. And so we go back to the Penn World Table on classification of systems, statistical systems. So there you have the list of countries in each of the groups. And you see that our misstatement, estimated misstatement of GDP, so the difference between our best predictor of GDP and the GDP reported by the statistical system, can be very small in some cases. If you click fill, I will be highlighting a few results for people to pay attention to. Please click again so I have the animation. Yeah, so you see there are countries that seem to have very good systems. Australia or Switzerland have very good systems. But you have countries like Ireland where there is all this issue of how they are computing the economic activity from the IT companies, where you have a very significant measurement error. So you can question the GDP figures of Ireland. Click again, please. Then you see countries that are classified as B, but they have a very significant measurement error, like Greece. Again, click. One more, please. And you have some countries that are classified as B, like Israel or Korea, that have very good statistical systems. They should be in group A. And then click again, just one more or two more, 5 minutes only, please. Yeah, and then you have some of the countries where climate change may have a very significant impact, where really the measurement error can be very significant, and others that again seem to be relatively misclassified. So one of the results we find is that the classification that everybody uses, or a lot of people use from the World Penn tables, is not that reliable. It's based on institutional indicators. This is a statistical way to look at the quality. Next slide. We see differences between the reported change in GDP and our estimate. You see there is not much of a difference in a case like USA, but we see it in the case of China. We see something that looks like an overestimate by the reported figures on GDP growth. Next slide. It becomes much worse when you go to conflict countries, to developing countries. You see that the two lines can be extremely different from each other. Next slide. In countries that suffer from economic crisis, in fact, the motivation for this paper was to try to understand what was going on in Venezuela. And what we found is that quite often estimates of economic activity that are reported are more tainted by perceptions than by actual data. We found that the figures that were being reported by the international community of Venezuela were more or less suggesting declines in output comparables to those that Germany suffered in 1944 during World War II for several consecutive years. And we thought that may not be too credible. And our data suggests that indeed there has been some overestimation of the magnitude of the crisis, huge, but not as huge as is said. Next slide. We see with the pandemic, that's another shock, perhaps more comparable to the extreme weather events. These shocks more localized in time. And you see that there is understatement of what happened with GDP in some countries, overstatement In others, and even in advanced economies, you can have significant errors. Look at number 31 on the left panel, the United Kingdom, and number 34 on the right panel, the US. Next slide. And so, given where I am in time, there is I will just give the headlines on future work, and this is something that probably Daniel will be picking up as a panelist. Just one slide, and I finish here. The next one. So the things we are considering is there are better measurements of NO2 emissions available now by the European State Agency. What we did was with the NASA data. Next slide. There is the issue of higher seasonality. We have been talking about annual data. We have estimated things for annual data, but there is a possibility to go into much more granularity. And again, if you think of extreme weather events, that's very important. Next slide. And then subnational. We have several very large developing countries for which just using national GDP can be very misleading for a lot of the most relevant shocks. And these are some of them. And next slide is we finish. Thank you very much. And again, sorry for my clumsiness with the slides at the beginning.
Hi, Martin. Thank you very much. So you did a very good job on the timing. So I just posted some questions here. And the first one, there might be a high linearity between nighttime data and NU2 data. The second one is you probably are using cross-sectional data, not time series data. So the time series data, if you use the time series data, the relationship between the GDP and also the NO2 might have it's not linear relationship. So like some in China and also some other developing countries, in some stages, there's a positive correlation between the GDP and also the NO2. But the later once they develop the stage, this relationship might be negative.
So thank you for these points. They are important. We use panel data. So we have, as I said, we are using controls for country effects, for time effects, and for satellite in the case of nightlight. So we use a panel structure. It's not always a balanced panel for all the countries. We explored the issue of non-linearities, and I think that was done also in the case of nightlights. And I think as an approximation, what we find is quite good. But indeed, there are refinements to be made. And I presume that as we move to subnational, those heterogeneities and non-linearities will become more important.
Great, thank you. We can have one question from our audience. You can open your microphone if you have any questions or noise.
Thank you for the talk. I'm curious. Do you expect, maybe this is an optimism tinted question, but as some of the power generation in countries begins to move away from fossil fuels combustion, that it might decouple the GDP from what you're measuring from the satellite imagery?
Yes, I completely agree. That's a very good point. Is that there are changes in the mix that we are not capturing if we don't allow for in the mix of outputs of technologies of sectors. So electric vehicles is an example.
Okay, thank you. So we can next speakers is Professor Daniel Riera Creighton, and Daniel received his PhD in economics from the University of California, Santa Cruz in 2007. He's currently associate professor of applied economics at Bates Carnegie. He also held research positions at the IBF and also the Capizon Capital LLC, and also Barcelona Chamber of Commerce. His topic today is measure global economic activity using air pollution. Where is he?
Hi, thank you so much for the introduction. I have some slides by my notes, and if it's okay with you, my understanding is just maybe talking a little bit about the issues. I can share the slides. It's fine too. So let's share those. Again, thank you so much for the organizers. Can you see the slides? And hopefully we won't have the same issues.
Good.
Yeah, so thank you so much. It's such a great forum to discuss these issues and present our paper. Thank you, Martin, for doing the hard work of presentation, and for Laura to present such a wonderful paper on climate change and climate impacts on cyclones. Let me start off maybe just connecting some of the questions that they were pushed out, and think about the improvement of data measurement that Laura was talking about in the conclusion, and that Martin was follow up with the paper. We believe that we're very excited about this, new energy in the field, at least in econ, trying to search for alternatives to a measure that we knew from the beginning it was not great, which is GDP. We've used extensively GDP across, but if you teach principles of macro, immediately you go into, well, but it's not such a perfect measure, blah, 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 right? So finding alternative ways of measuring economic activity seems really important. We're excited about the opportunity the satellite measurement gives us. To us specifically, measuring relating air pollution to combustion and economic activity, it can give us real-time measurement of, for example, connecting to Laura's paper, economic consequences of natural disasters, localized economic consequences of natural disasters. Several dimensions to this. It's a temporal dimension, high frequency, and then there's a geolocation, right, dimension where we can just, like go subnational, sub-regional to local effects. And this could, help us better understand vulnerabilities for certain populations and apply better policy, especially now that climate change is affecting the frequency, especially the frequency and the intensity of the natural events that affecting certain communities more than others. No? Related to the question on, a very good question on, how kind of a time goes against us in the sense that, the productivity in units of pollution of economic activity is decreasing over time. Absolutely right. We need to think about our measure to help us in the short run, or the biggest gain, I believe, from NO2 or NOx gases is on the cyclicality, right? We're very, very good at picking up the cyclicality of economic activity. We're not that good at picking up trends, precisely because we have that downward trend going against us, right? We, as economies evolved and start improving the way they are producing in their economies in terms of pollution, well, that is kind of dissipating the relationship that we are using. But there are other things out there that are good at picking up those long-term trends, like lights. Night lights are a good measure. We don't think we are competing with night lights. We think that we are providing kind of a companion to night lights to better understand the whole picture. And using night lights, for example, could help us beyond going to the immediate impact of a cyclone or other natural disaster. It could help us also disentangle, what happened to that region over time, right? If it's, the growth trends, if we have migration away or on this vulnerable space, etc. So absolutely, we strongly believe that better measurement of economic activity and the dynamics that comes are going to provide important tools for policymakers to react to climate change events and to the climate change consequences. And we're excited to, continue to proceed developing those data tools. On the observation of economic change through our measure is again is really really important to understand the differences between the the cyclical part of the economic activity and the structural, the long run part of economic change. And we're going to need different tools. That's for sure. As one of our co-authors always like to say, if you lose your job, you are going to go home and still turn your light on, although you may not drive to home to the work the next day. So there are different ways to picking up different problems. We believe our measure is very good for at the point of measuring cyclicality, but it's not going to be good at for picking up those long-term growth trends. That could be also really important to understand good policy. We are going to have to deal with the fact that the productivity per unit of pollution is increasing. We have tools that we may incorporate into that. Again, this is not going to be an issue that's going to be solved tomorrow. So, and especially in developing countries, we still have a long way to move completely away from combustion in our economic activity. But as we transition, especially in advanced economies, we're going to have to figure out new tools to complement our analysis. And then on future work, Martin mentioned a little bit of it. There's the tools are becoming better and better and better. The original paper was built upon NASA data on a relatively old satellite. The Europeans have now satellites out there which provide free data twice a day with 5 times the precision for the estimate. So things are moving fast. More and more data is becoming available, and is good to dig into it and see what we can get out of it. I think there's 2 dimensions where this is helping us a lot, at least in macroeconomics. There's a temporal dimension, which we have access to very high frequency data, and there's a cross-sectional dimension, which give us access to subnational or even sub-regional data. On the temporal dimension, we have more than forecasting. We have an interest on looking at nowcasting. As Martin was saying, we have in macro we are waiting to learn about GDP data. It's going to take a long time. In advanced economies, GDP numbers in the very United States, the most efficient statistical systems out there, GDP data will come with a delay of at least a quarter. For good data, probably 6 months, and then there are going to be revisions to that data. In emerging markets, this could be as long as 1 or 2 years. And of course, think about my example here is think about you're sitting here in March or April 2020. COVID is out there, is ravaging it's ravaging your economy. Health policies dictate people need to go home, stop what they're doing. So there is a huge impact economic impact on this crisis. But if you are relying on GDP to tell your story, this is just going to be too late. So to be able to bring a good idea, a good proxy of what's going on the ground right away, within a week. Martin was showing the map for China. That map was, I believe it was last quarter of 2020, which is when the big impact happened in China, against last quarter in 2019. But we could have recreated that map to be a week apart, right? As soon as COVID was detected and spread out in Wuhan province, we could look at the evolution of that every day or a week apart. I mean, this is really high frequency that allows us to go into thinking more on this nowcasting, to understand what's happening on the ground right away. And this could be really, really helpful for policymakers. There's also that cross-sectional dimension, that geo dimension, where you think about an earthquake in Haiti, and you have no idea what's going on there. You can go into diverse emerging markets, but also subnational, sub-regional level data to understand exactly which communities have been affected the most, where the damage has been created, and which policy to apply, and the distributional side of the policy as well, right? How to apply them best. So we are really excited with this. And I think that Laura is completely right. We need to look into combining this new empirical approach, new techniques, new tools, new high frequency, more localized data into our theory to understand better what's going on. I'm gonna leave it there. I don't want to overstand, and I'm happy to discuss more as needed. Thank you.
All right, thank you.
It's for our next panelist, Dr. Luis Eloy. And Luis is a dear colleague at George Mason University in the AOES Department of Atmospheric, Ocean, and Earth System. I don't know if I captured all of this, Luis. He's a rising star in our AOES department and also in the climate change community. And he's leading the establishment of an NSF IUCRC for the insurance industry. And he's going to talk to us about that. Luis, please go ahead.
All right, thank you so much, Phil. Let me share my screen and fingers crossed I click on the right thing. Are you guys able to see my presenter slide? Fantastic. So thank you so much for the introduction, and Phil. I don't know about rising star, maybe a guy who can't say no to things. I think it's a better description. But today, going to be perhaps shifting gears slightly, and maybe talk to you all about this sort of emerging set of activities we have going on, which is a collaboration. It's based out of George Mason University, and not just in my Department of Atmospheric, Oceanic, and Earth Sciences, which I think it took me like 3 months to say it right without tripping. But also we have other sites for this emerging sort of activities at Massachusetts Institute of Technology and the City University of New York. And excuse me, what we are building is something called the Center for Climate Risk Applications, or CCRA. Which is an industry university cooperative research center. It's a sort of unique funding mechanism under the National Science Foundation because the government, the federal government under NSF funds the administration of the center. And then the rest, all the research under the center is actually funded by industry partners. That it's our job to recruit and entice with fantastic research products. So I'm going to be talking to you all about what our current thinking is around the needs of a particular industry. Which is, or a particular sector of the economy, which is the insurance, reinsurance, and financial sectors. We are sort of addressing a targeted call for centers addressing how climate change is impacting the prediction of hazards and risk from the point of view of these industries. I think it's not an overstatement to say that a lot of these companies are in trouble. It's all over the news, and it's impacting people whose premiums are going up. It's impacting companies who have to back out of particular markets. Big news a year or two ago, Florida, some insurance companies leaving Florida because of all the emerging climate-related risks. So before I get into all that, I would be remiss if I didn't say a little bit about all of us as a group. As Dr. Yang mentioned, I'm leading the center out of GMU, and I come with expertise on urban climate and extreme heat. But more broadly, at George Mason University, we bring decades of fundamental climate dynamics research in the form of the Center for Ocean, Land, Atmospheres Studies that is based at George Mason University. But we also have tremendous expertise on climate adaptation, mitigation, modeling extreme events, all the way down to climate finance and policy. On the side of MIT, we are led by Dr. Adam Schlosser, who is one of the leads in the MIT Center for Global Change Science. And he's a deputy director of the joint program at MIT. And they bring all expertise on global scale modeling, assessment of climate change impacts, multi-sector impacts. And then on the CUNY side, we are partnering with the NOAA-funded Center on Remote Sensing. So they're bringing in massive expertise on both spaceborne remote sensing as well as ground-based remote sensing to sort of get at what some of the vulnerabilities on the ground and the distribution of some of these hazards might look like. So why these particular industries? Why climate change? Why natural perils? Why is NSF and NOAA putting out these massive efforts to try to fill in fundamental research gaps? Well, as I said before, climate change is changing the frequency, intensity, and the impacts of a variety of natural hazards. And on top of that, it's also making our ability to predict those hazards in the future much more difficult. It used to be that we were able to take a historical representation of some hazards and look at the distribution, kind of sort of like part of what one of the earlier presentations was, and then draw reasonable inferences about what those hazards might look like today. What's happening is climate change is changing the baseline or the base state of the atmosphere, and it's changing all these characteristics of the distribution of all these hazards. Essentially, they're becoming non-stationary as a result of our changing climate, and that places a lot of challenges, both on the impacts and on our ability to predict them. So our pitch to build the center and to help fill some of those gaps is to conduct fundamental research that addresses gaps in that we have in prediction of those hazards, and then look all across that value chain beyond the hazards, looking at vulnerable assets through Earth observations, or even vulnerability through various other engineering-based methods. Someone mentioned damage curves earlier, stuff like that. We also want to be able to essentially tackle issues related to policy and how that might affect the ability of these companies to price their products, which is really the challenge at the end of the day. As a note, even though this is a center that aims to serve the needs of a particular industry sector, we are not a consulting group. All the research we conduct is what NSF calls pre-competitive. And what that means is that it's of general value and interest for a whole industry, rather than conducting some particular analysis for company A or company B. In fact, we are expressly prohibited from doing that kind of work under the umbrella and the funding provided by this center, funding that comes from the companies. So I want to do a little bit of a I won't call it a deep dive, but at least a review or overview of what some of these issues and what we've been hearing through our extensive engagement with the insurance, reinsurance, and finance sectors over the past year. I think this is the one thing that almost every person we talk to mentions. There's a lot of pain around, or a lot of incongruency between the data products that we have today related to climate hazards. A lot of them are designed from general circulation models or Earth system models that are really meant to represent the long-term change in the state of the atmosphere and everything that happens in the atmosphere. So looking at 30-year time slices, or and perhaps looking at some of the extremes, the changes in extremes in those time slices, and looking far ahead into the future. However, that's not the timelines that these companies can even operate in often. You have to price products for next year. You have to price products for the next season. It is very difficult to do that. In fact, there's a big gap in our ability to predict sort of this sort of in between time horizon in between weather and climate. We're relatively good at predicting weather, up to like 10, 14 weeks ahead of time. We call that weather forecasting, and we're pretty good, reasonably good at sort of that long-term, 30-year climatological scale. But then once you start getting into a season or into a year, then it becomes very, very difficult. And that's due to a variety of reasons. One of them is the way that error or uncertainty propagates in the atmosphere fundamentally at a fundamental level. Information sort of propagates through the air, and there's turbulence and all this stuff happening. Even if we were to have perfect observations of the Earth, which we don't for everything that we need to, we would not be able to predict perfectly. That's a very fascinating area of work that came out from the 70s and 80s out of groups out of MIT and even out of George Mason University. But again, those are not the timescales those are not the timescales that we care about far in the future. We care about next year. We care about the next season. And there's a lot of improvements that need to happen in the next set of years. And not only that, but when we work with ensembles of models, you can often have disagreement between them. So addressing that is another source of pain for these companies. I'm showing here on the right a 4-panel figure of maximum one-day precipitation for a variety of climate scenarios by end of century. And anywhere where you see a hatched mark is where the noise is larger than the climate signal. So for precipitation, you can see there's a lot of shaded areas. Okay, so I will rush through the rest. The other problem we hear about a lot is convective storms. We just heard about tornadoes, which is a type of those. It's the top loss leader in insurance industry in the first half of this year. They lost $60 billion in the US this year, 70% of their total. Talking about hailstorms, tornadoes, thunderstorms, not hurricanes, which we just saw a huge one in North Carolina, our neighbor to the south, but rather smaller storms, which require much higher resolution to resolve the fundamental physics of what's happening with them. And then there's a big issue, both regulatory and in the companies in how can they know what's going on behind the scenes in the creation of data when they get data from data providers, for example. How are they processing that data? Why are they so different, the products between the various data providers? So there's a need for benchmarking all these solutions, including the public-based ones from the government. And there's also a need to test and use emerging technologies like machine learning that have been coming out that to sort of create new forecasting workflows that use the physics-based modeling that we've traditionally used, but perhaps improve upon it by letting us run giant ensembles for very little training time, or sorry, for really little computational time. So I will stop there, and happy to answer any questions or address any comments people might have.
We're going to have a panel discussion. So any remaining questions you have for our speakers, please feel free to bring them up. Just as a warm-up, this question could be for everyone. Obviously, when we do our research, you look at who are the users, who are the stakeholders. One question we always ask ourselves in terms of research is that how far are the current research from the end users' needs? For example, Luis, probably the insurance company, what do they need? And what could we produce? And what's the gap over there? Oh, versus Nora, if the policymakers wants to take some kind of financial decision based on the country differences on the hazards impact on the economy. So what is current research towards that information need, actionable information? Yeah, so please go ahead, respond to that.
Well, I'm happy to kick it off. On our end, there are some fundamental challenges in how we address the needs of these companies, or at least this sector of companies. One of them is we do have prediction capability, addressing those sort of that gap that I mentioned earlier. What seems to be less available is taking this data from NOAA, the government, and turning it into products and doing the science that turns that into products that they can use. It's one thing to take data from make it available from a GCM, from a global climate model, and it's another thing to provide a distribution of hail, storm, pellet size for companies. There's a big gap between that, and there's some fundamental research needs to happen there. There's a lot of the pieces are already there, but I think there's a lot of research that still needs to be done to fill in some of those gaps, including the high resolution downscaling that would allow us to take that information and sort of add all the missing pieces to it, if that makes sense.
And the research that we conducted with Daniel, and we're still embarking on, the end users, I believe, are an entire industry that works on forecasting. That's the most obvious group. There are people who have all sorts of leading indicators and statistical tools whose value is very high. If you can understand what is going on with the economy and understand earlier than others what will happen with the Fed's decision and the interest rate or whatever it is, there's a lot of money that can be made. So there is a clear interest in having better ability to measure in real time what is going on. And the next step of our research is clearly to run like horse races between the different models and estimates that like leading indicators and others to, we believe, show that this kind of information is more accurate and more timely, and therefore has value. So we believe that there is a demand there that could be addressed in a more academic way through research, but is also a commercial demand.
A couple kind of thoughts that came to mind with regard to the paper that I presented. I think two things. One, while the kind of final end results probably are a little coarse for what a policymaker would really want, I think some of the pieces of the overall analysis can be very insightful. So for example, not this particular, so the wind elasticity of damages in the United States, I had actually examined that also in a previous study, and the Congressional Budget Office wanted to do some of their own analyses. So then they were able to go into some of these economic analyses and in fact pick that particular parameter to then kind of calibrate their own model. So I think a very, the full model may or may not be exactly what the policymaker may need in the end, but I think pieces of it, parameters of it, and also understanding these feedbacks and interlinkages, which kind of leads me to my second point is, I think one of the things that have come up in our discussions today, even thus far, is the public and the economy's responses, right? Their responses to policies, their responses to changing, shifting risks may be very different and may be heterogeneous. So I think also, using these types of models to give insight to policymakers about these are the types of industries or sectors or individual decisions that we may see a plethora of responses, and that may dampen or intensify the policy responses, potentially in unintended ways. So I think those are also some kind of broad take-home messages that I think policymakers are particularly interested in.
Thank you. Daniel, please go ahead.
I'm sorry. Yeah, I said that it is also noticeable, at least from our side, the challenges that involves this type of data in terms of transform it from where the scientists are to where an economist can grab it and just use it. And it is not straightforward at all. I mean, and no blame on the scientists. The scientists will do a wonderful job cleaning the data, giving us all the information. Most of the data we use is freely available, which is crazy. I mean, this is just it's just the sheer volume of the data, how to manage it into something that an economist could put in a model and run it. It is something that we are still working on, and it's not obvious, it's not there yet as a standardized method. And if it's one researcher needs to do it by itself, it may be too much to apply it at this point. So more of effort on that, kind of a conversion from where the data is right now to something that's usable could be definitely useful.
Thank you. So for everyone, if you have any question, please put it in the chat window, or you can unmute yourself and speak.
Hi, I'm Sridhar from City of Virginia Beach. And so one of the key things what happened in the last 2 years was FEMA has changed their whole system, and they made now something called risk rating. I think they call it as risk rating or 2.0 or something, where they changed the complete dynamics. So what they were doing there was prior to that, the flood zones were provided as A, E, and everything, and X was a zone where you could get preferred risk policy for 1/3 the cost or 1/4 the cost per year for you to do that. I think when risk rating 2.0 started, after that, they started providing that these are the few percentages are increasing or decreasing. So in my case, what I've seen was it increased 4 times. So why it increased 4 times was, so they have used a model called cat risk. I think it's out of California. So that came out around 3-4 years about doing supercomputers, used supercomputers for 50,000 hurricanes modeling, and then the probabilistic. And then what they did was they used new methodologies in that. So all the X zones were not X zones anymore. So they started falling into AE zones. And then they removed the complete preferred risk policy. So now I think it's sometimes a lot of times you'll see a lot of higher costs in per year for these zones. So in our city, we have several X zones. So most of them think that they're an X zone. But in the new risk rating 2.0, you see you're completely in a different world now. And that's an example, practical example of the difference between what is coming and what we are seeing on the ground. And currently I think it's not that is provided, because that itself, the X zones and all were done a long time back and they had gaps. So in the new model, there are other gaps also you might be finding in research. So anyway, that's a thought on that.
Do we have a response from our panelists to that?
I guess a quick thought, and you said you're in Virginia Beach, which suffers from chronic flooding, right? Even sunny day flooding. There's been a lot of concern whenever they update the flood maps. It happens everywhere. I work a lot in the city of New York as part of the New York City panel on climate change there, and I remember kind of clearly that when FEMA updated the flood maps, they pushed back against them. They said we can't do this, because it implied a lot of increases in cost in very expensive areas. So you can imagine they were not very happy about it. But on the flip side of that, you have to price risk adequately, right? In order for the insurance system to work. So I don't know if there's a need for maybe transparency on how these insurance products are priced and how that's communicated to the public. Because at the end of the day, people see a bill related to their flood risk, but they might not know why, right? Or they might just be told, oh, you just sent a bunch of letters, right, related to the flood risk, and various entities might not know what those mean necessarily, right? And they just see a higher bill and get upset about that. But so there's this sort of double-sided, two sides of the same coin, this communication and transparency that needs to happen. But yeah, I don't know what a potential solution there is, because the risks are increasing in many places, right? So we have to be able to price those in some way.
Yeah, there are two sides of that coin. I think the first is when I investigated that is to call the insurance company, this was State Farm, and then ask them, and then they would say, okay, you are not in AE, so you're not in X zone, you're AE zone. And I asked them, oh, I'm seeing one thing and you are seeing another thing, and what is that? So they dug into it, and then they came back and told me, okay, this is increased this much, and your CRS rating is this much, and this is your. So that was the big leap which happened between risk rating 2.0 versus the below. Then I started investigating all that area, how now you're not seeing that relationship of risk rating 2.0 with your parcel to be as a system that you can see on a map now. Now you are provided with a value of this much you are going to pay. So that's how that whole dynamics have changed completely.
I think one thing I'll add quickly, because I think you've really characterized well the kind of state of the National Flood Insurance Program reforms, and the long-standing tension for fiscal solvency versus insolvency. Since about Hurricane Katrina, the program has been pretty fiscally insolvent, where they take in fewer premiums than claims paid out. Unlike what Luis was very eloquently describing, the demands on the private insurance industry, and how they don't have the ability to run multi-year debts, essentially. So I think, it also, so I think one of the statistics about 65% or more of policies will see increases in premiums under risk rating 2.0. I think a couple interesting themes from my perspective is, one is, the variety. I think you're alluding to, like, there's a lot of variety of even flood risk information at the local level, right? And Luis was highlighting some of the real challenges in this, spatial and temporal precision in these predictions. But we can see, official FEMA flood maps versus organizations like First Street Foundation that have kind of alternative products, and think that there's almost double the flood risk. So I think it'll be a really interesting movement forward about how these different sources of essentially what should be quantifying the same fundamental risk, how the variation will kind of play out across markets. We're seeing things like First Street Foundation risk factors embedded in Realtor.com, Zillow.com recently incorporated them too. But the interesting thing is, as you're also showing, FEMA's information, so their flood insurance rate maps, have regulatory power, and therefore they have a lot more legal scrutiny in the precision of these, right? So as we know, it's probably much easier to show something might be wrong or faulty, rather than really, not prove, of course, but like, show the very high quality mapping. So I think that's why we've seen so much litigation surrounding some of these particular subsets of climate risk products that really are scrutinized, legally, because of their political regulatory role in managing these risks. And then one more quick comment. I think what this ultimately, a big question of interest right now, I think, to federal regulators is who's bearing these climate risks ultimately, right? If the private market can properly price in the climate risk, it kind of, they can offer an insurance product, but that kind of puts the risk back on the individuals, the homeowners. Of course, if mortgages are involved, then oftentimes banks or the government will require some of these insurance products. But I think there's also interesting cases where the disaster risk may not be well insured. So as you're showing, flood risk outside of the mandatory flood risk zones, earthquake risk, not quite a climate risk, but still a significant, very uninsured or underinsured risk in the housing market. And this can then transfer risk to things like mortgage lenders or government-sponsored enterprises, depending on who's owning some of these mortgage products ultimately. So anyway, long-winded response, but I think you're bringing up some really, key questions right now in kind of at the macro level as to, who's, how are these risks being priced, how the variation in our understanding of these risks and ability to model them, and then who ultimately will bear these costs. And I think, one last little arm, I think a really fascinating insurance is the interplay between public and private insurance. So in what areas private insurance feels comfortable in a regulatory regime offering insurance products in order to price in that risk versus other areas that they may not. And so we've also seen for some particular peril hazards, state level insurance schemes like lenders of last resort, for earthquake, for flood, for hurricane, not for flood, sorry, but for hurricane wind. So I think that's going to be a really another interesting question about, fiscal solvency of all of these different types of insurance products and how they're thinking about and pricing it, and who ultimately is bearing these risks.
Yeah, thank you all. That's a very broad discussion about the change of the flooding. When you go to different granularity, that's always, especially when it gets to actionable information, there's a lot of invest has to go in there. Let's switch the gear a little bit. We heard that Luis was saying that, okay, these geophysical models help us forecasting the climate disaster maybe in the next year, 2, 3, or 10 years. So that could help us project the insurance demand. And also for both Laura and Martin's research, you used statistics. These are all kind of math-based or the geophysical based. Do you see a need? Discussion about the AI machine learning models. Would AI machine learning be helpful to the research that you are conducting when it comes to economic?
Yes, I go first. Yes, it's in short, but it's there are two big parts of that. One of them is a lot of these newer machine learning based models have shown incredible fidelity. They're all trained on the physics based models, so at the very least they are able to represent that, and they've even shown some very good skill at several forecasting workflows, including short-term forecasts, like 7 days ahead of time. Where I see a lot of potential is in our ability to create probabilistic forecasts using very large ensembles. So running a physics-based model is an incredibly expensive endeavor. You need a supercomputer. You need to run it for many hours to obtain a single realization. And there are some efforts at NOAA, the Europeans at ECMWF have their own ensemble forecast based on physics simulations. You essentially perturb the model a little bit and then see how that changes your forecast, and then you present an ensemble. And the machine learning products now allow you to do 10, 100, 200 ensemble members that really let you fill in that distribution of whatever hazard you're looking at. The flip side of that is, because it's so opaque, the guts of those models, you really have to test whether they're forecasting the one thing you are interested in very well, and look at the entire distribution. I think Laura was mentioning that a little bit earlier on the tracks data, and you have to test that for basically everything, right? Is it modeling the extremes well? And we care about the extremes, right? They give us the highest costs often. So testing that is something that's going to be an emerging set of activities, I think, especially because every company and their mother are starting to put out all these models, and we need a way to evaluate them in an apples to apples comparison.
Yeah, I think those are great points. I think thinking about the end use for machine learning or AI, so thinking about prediction or forecasting, if you really just care about that end number, I think there's a lot of optimism around machine learning to be able to provide at lower cost or lower computational abilities some of these ultimate predictions. But when you start to think about it, I think there's opportunities, but I think it's just we have to be very thoughtful about how they're applied when we're using machine learning to predict or forecast counterfactuals. So not just, based on what we've historically seen in projecting forward, but, thinking about some of these very relevant counterfactuals about future states of the world or future decisions. And again, I think we just need to use a little bit more thought when applying it. I'm not saying that they can't be. There have been some nice papers that have very thoughtfully looked at counterfactuals. And then also, I think exactly as Luis was saying, thinking about they're mainly atheoretical in how they're generating their predictions and forecasts. And so I think we need to also think very carefully about how and when we're building our theory and to what extent or how machine learning and some of these really cutting edge techniques can help. Making sure we're not misinterpreting or kind of misunderstanding. I think, it potentially could lead us to understand new relationships that we never realized, and then we can kind of go back to the theory and revise as well. I think there's a lot of exciting potential, but, as somebody who also thinks that things like, grounding empirics in theory and things like that can be really illuminating as well. So I think all of the approaches will help to make advancements when they're appropriately used.
Well, thank you, Luis and Laura. I saw that Chunying and Magneto is also joining us. Do you have anything you want to add to that? Because you have a deep research and investigation on AI machine learning to climate change. Or maybe not. Dr. Luis, I saw that you're muted. Do you have any question or any thoughts you want to share?
No, I just really enjoyed listening to the presentations. In addition to being a professor and being a co-PI on several of the projects that Dr. Yang directs, I'm a planning commissioner in the city of Fairfax. And we really struggle sometimes to figure out how to incorporate things like revised FEMA flood zone boundaries within the economic decision making and development within the city. So I enjoy kind of listening to scientists and then thinking as a scientist about how I would apply some of the lessons learned to real world situations. And so anyway, I've enjoyed this a lot. I don't have any other comments. Thanks.
Thank you, Dr. Luis. I saw that we also have several distinguished guests joining us today. Dr. Mei Yuan, are you there? She's quite busy. She's probably in another meeting. Oh, she's here. Yeah. So, Mei, thank you for joining us. Now you heard about the gap of research and challenges we have in estimating the economic challenges and changes because of climate change. Do you think there's any NSF programs that we could target?
I would say that the climate change is one of the strategic research themes for the entire agencies, and is under the umbrella of building a resilient planet. So there are a lot of programs. It's hard to really enumerate, but almost every SBE programs will entertain climate change proposals, especially HECS, the Human Environment and Geographic Sciences, and also the Decision, Risk, and Management Science in SES. And then we have a constant communication with Geo, Bio, and sites on climate change related issues. So I think that depends on the focus is on the computation or technology development, or is in decision making, risk assessment, or in looking at human societal impact and geographical variability and drivers, and different programs will be most appropriate. Look, NSF program directors like me, we are public servants. So anybody interested in submitted proposals, you can reach out to any program directors, and we will help you to identify which program will be most fitting to your research ideas. And if you don't know who to contact me, please, and I will be more than happy to help out.
Well, thank you, May. It's really great to have you here and share with us that. And we'll be in touch with you. So everyone, if you have any idea you want to propose to NSF, and you don't know anyone to contact, yeah, please reach out to Dr. May Yuan.
And let me put my email address on the chat so that you know how to reach me.
Yep, please save that email and for your potential next funding opportunity with Dr. Yuan. Okay, we're about the time. Really appreciate our speakers. Thank you, Laura, and Martin, Daniel, and Luis. And also thank you everyone for joining this webinar. And we're going to continue this digital twin webinar into November and December. We will announce that and send the calendar invitation to you all. Thank you, everyone.
Thank you.
Thank you, everybody.
Bye.